Half the normal matter in the universe has simply vanished. This is the missing baryon problem, one of astronomy's greatest modern puzzles. You are about to join a cosmic investigation, following 25 distinct clues that are leading scientists to an answer. We will trace the trail from the afterglow of the Big Bang to the invisible filaments of a million-degree gas web, uncovering how cutting-edge tools like fast radio bursts and X-ray telescopes are closing the case. By the end, you will understand exactly where the universe has been hiding its atoms and how we are on the verge of finding them all. What does it feel like to finally solve a mystery that has haunted cosmology for decades? Our cosmic ledger has never quite balanced. This is the first and most fundamental clue, the discrepancy that launched the entire investigation. After the Big Bang, the universe left behind a very specific blueprint, a fossilized imprint of light known as the cosmic microwave background. By reading this ancient light, scientists can calculate with incredible precision how much normal matter, the stuff that makes up you, me, planets and stars, should have been created. This normal matter is called baryonic matter, named for the protons and neutrons that form the core of every atom. These are the building blocks of everything we can see and touch. The calculations are clear and they are firm. They tell us exactly how many baryons the universe started with, so scientists began the monumental task of taking a cosmic census, adding up all the baryons they could find in the modern, nearby universe. They counted every star in every galaxy, every planet, every speck of cosmic dust. The final tally was a profound shock. All the visible matter accounted for only about half of what the models insisted must be there. Imagine carefully budgeting for a grand project, only to discover half your materials have simply vanished from the warehouse. That is the scale of the problem. Half of the universe's normal atoms were missing. This was not some minor accounting error. It was a gaping hole in our understanding of cosmic evolution, a fundamental question that challenged everything we thought we knew about where the universe put its stuff. If we could not find this missing matter, we could not truly claim to understand how the universe works. So where do we find such a precise recipe for the universe's contents? The answer lies in the oldest light we can see, a fossilized echo from the very dawn of time known as the cosmic microwave background. This faint glow permeates all of space, the cooled remnant of the universe's hot, dense infancy. For scientists, this afterglow is not just a uniform curtain of light. It is a detailed map, a cosmic ledger written in the language of temperature. By studying the incredibly subtle variations in this background temperature, tiny hot and cold spots smaller than 1 part in 100,000, cosmologists can decode the exact conditions of the early universe. These minute fluctuations are like the universe's own fingerprint, encoding fundamental information about its composition, its shape, and its ultimate fate. They tell us precisely how much dark energy, dark matter, and normal baryonic matter the cosmos contains. The calculations derived from this ancient light are astonishingly precise. They give us a specific target, a number that represents the total amount of baryonic matter that must exist today. Think of it as the universe's own packing slip, a definitive list of the materials created in the Big Bang. Our mission then becomes a cosmic scavenger hunt. We are not guessing how much stuff is out there. We are holding the original blueprint and searching for where it all went. The modern universe must contain every single baryon counted in that primordial light. The mystery is not whether they exist, but why we have only been able to find half of them. This sets the stage for a true detective story where the clues are not just in what we see, but in what we cannot. The search for this cosmic inventory leads us to a tool of astonishing subtlety. We must learn to read the shadows. When astronomers point their most powerful telescopes at the most brilliant beacons in the universe, quasars, they are not just looking at the light itself. They are studying what happens to that light on its billion-year journey to Earth. As the intense beam from a quasar travels across the cosmos, it passes through countless clouds of invisible, diffuse hydrogen gas. This is not the cold, dense gas that forms stars. This is a wispy, almost ethereal medium that fills the vast expanses between galaxies. Each cloud of hydrogen it passes through leaves a distinct, dark fingerprint on the quasar's spectrum of light, a specific absorption line known as the Lyman-Alpha line. From a single, distant quasar, we do not see just one line, we see thousands. The resulting pattern is so dense and intricate that scientists call it the Lyman-Alpha Forest. Each dark line in this forest is a shadow, a ghostly imprint from a specific cloud of gas the light encountered. By carefully mapping the spacing and depth of these lines, astronomers can perform a kind of cosmic tomography. They can reconstruct the three-dimensional distribution of this invisible hydrogen gas. They can measure its density and even trace its velocity. This forest is not a chaotic tangle. It is a structured record, a detailed map of the cosmic web's finest threads. For detectives on the trail of the missing baryons, this is a gold mine. The gas revealed by the Lyman-Alpha Forest is incredibly diffuse and far too cold to emit its own visible light, making it completely invisible to traditional telescopes. Yet the sheer volume of space it occupies is staggering. All these countless, wispy clouds add up. Could this vast, shadowy reservoir of hydrogen be the hiding place for a significant portion of our missing atoms? The evidence was starting to point in that very direction, suggesting we had been looking for the wrong kind of stuff in all the wrong places. But the Lyman-Alpha Forest, for all its revelations, could only account for a fraction of the missing mass. The hunt needed to narrow to focus on a more elusive suspect. The leading candidate is a ghostly realm of unimaginable scale and heat, a theoretical structure known as the Warm-Hot Intergalactic Medium, or the WHIM. This is not a collection of cold, dark clouds. Instead, it is a vast, searingly hot web of gas stretched across the cosmic voids between the great galactic filaments. The temperatures here are staggering, reaching millions of degrees. At such extremes, the gas behaves in a way that makes it nearly invisible to our traditional tools. It is too hot to glow in visible light and too diffuse to cast the kind of sharp, dark shadows we see in the Lyman-Alpha Forest. Think of a bonfire on a distant mountain at noon. The air shimmers with heat, but you cannot see the distinct flames against the bright sky. The WHIM is the universe's version of that shimmer, a pervasive heat haze on a cosmic scale. Its atoms are ionized, stripped of their electrons, and spread so thinly that a single cubic meter of this space might contain only a few particles. You could fly a spaceship through it and never know it was there, yet its total volume is so immense that it could easily hide the entire missing half of the universe's normal matter. For detectives on this cosmic case, the WHIM became the ultimate smoking gun. All the clues pointed to its existence. The laws of physics demanded that a large portion of the early universe's gas should have been heated and swept into these vast intergalactic rivers by the force of gravity and the shockwaves from exploding stars. Finding a way to see this invisible web, to prove it was really there and weigh its contents, became the next great challenge in closing the case. Detecting a million-degree gas web requires a very special kind of vision. Ordinary telescopes are blind to this searing heat, but our most powerful X-ray observatories like Chandra and XMM Newton are built for this exact purpose. They see the universe in the high-energy language of X-rays, the same kind of radiation used in a doctor's office to see through skin and reveal the bones beneath. In the cosmic context, these telescopes are our X-ray vision, allowing us to peer into the seemingly empty voids and search for the faint, telltale glow of the WHIM. The gas itself is so thin it barely emits any light at all, but it is not completely empty. Scattered within this hydrogen and helium soup are trace amounts of heavier elements, atoms like oxygen and neon. forged in the hearts of long-dead stars and blasted out into intergalactic space. When heated to millions of degrees, these atoms become highly ionized, stripped of many of their electrons. It is the frantic dance of these remaining electrons, jumping between energy levels, that produces a faint but specific signature in the X-ray part of the spectrum. Catching this signal is one of the most delicate tasks in modern astronomy. It is like trying to hear a single violin playing a perfect, quiet note from within a roaring hurricane. Scientists point these incredible observatories at the blank spaces between galaxies, collecting X-ray photons for days or even weeks on end. They are not looking for a bright picture. They are assembling a statistical whisper, a slight excess of photons at very specific energies that corresponds to the fingerprint of ionized oxygen. Sometimes they use a bright X-ray source in the background, like a distant quasar, and look for the shadow of that same ionized oxygen as it absorbs the quasar's light on its journey to us. Each successful detection, each faint line in the X-ray data, is a monumental achievement. It is the first indirect glimpse of the cosmic web's hottest threads, a ghostly tracing of the universe's hidden architecture. These observations confirm that the WHIM was not just a theoretical idea. It was real and it was out there, but simply knowing it exists was not enough. We needed to know how much it weighed. Could this hot, thin gas truly account for all the missing baryons, or was it just another piece of the puzzle? The hunt was narrowing, but the ultimate proof required an even more precise and universal measuring tool. There is another way to see this ghostly web of hot gas, one that uses the oldest light in the universe as a cosmic flashlight. This technique relies on the Sunyaev-Zeldovich effect, a subtle interaction between the present and the primordial past. The cosmic microwave background, that ancient afterglow from the Big Bang, fills every cubic centimeter of space. It is the most perfect and uniform background radiation we could ever hope for. As these primordial photons travel for billions of years, some of them pass directly through the searing hot gas of the WHIM. Inside these vast clouds, electrons are moving at a ferocious speed, energized by the extreme heat. When a cold, ancient CMB photon happens to collide with one of these fast-moving electrons, something remarkable happens. The electron gives the photon a tiny kick, a boost of energy, like a ping-pong ball being struck by a swinging bat. This interaction, known as inverse Compton scattering, leaves a distinct fingerprint. It subtly changes the character of the CMB light that passed through that specific region of hot gas. The cold, low-energy photons from the early universe are boosted to become slightly hotter, higher-energy photons. This creates a very specific, minuscule distortion in the CMB's signature. We cannot see this distortion with our eyes or even with a single glance from a telescope. It is a statistical ghost, a pattern that only emerges when we look at the data from enormous sky surveys. Astronomers compare the pristine map of the cosmic microwave background with the locations of known galaxy clusters and the vast empty spaces between them. They search for these telltale distortions, these tiny patches where the CMB appears just a little bit warmer than it should be. Each detection is like finding the shadow of an invisible giant. The effect itself does not show us a glowing picture of the WHIM. Instead, it reveals its presence through its imprint on something even more fundamental. It tells us with statistical certainty that a vast reservoir of hot, ionized gas is right there, warping the oldest light in the universe. By measuring the strength and extent of these distortions across the sky, scientists can begin to weigh this hidden component of the cosmos. It is a brilliant piece of detective work, using the universe's first light to illuminate its darkest secret. While the Sunyaev-Zeldovich effect uses ancient light as a backdrop, a new and incredibly powerful tool for probing the cosmic web has emerged from one of the universe's most enigmatic events. Fast radio bursts are millisecond flashes of intense radio waves that travel billions of light years from distant galaxies. Their origins are still a mystery, possibly involving supermagnetic neutron stars or cataclysmic collisions, but for cosmologists, their greatest value is not in how they are created, but in the journey their signals take to reach us. As a fast radio burst travels across the vast, near-empty expanses of intergalactic space, its signal does not arrive all at once. The burst is composed of many different radio frequencies, and each one interacts ever so slightly with the sparse sea of free electrons it encounters along the way. Higher frequency waves travel just a tiny bit faster than the lower frequency waves. This causes the signal to smear out, to disperse, like a prism spreading white light into a rainbow, but over an incredible cosmic distance. The key insight is that the amount of this smearing is directly proportional to the number of electrons the burst has passed through. More electrons mean more dispersion. And since every atom of normal matter, whether in a star, a cold cloud, or the searing WHIM, contains electrons, this dispersion measurement becomes a direct probe for the total amount of stuff between the burst and our telescopes. Think of it like this: you are listening to a drumbeat from a faraway mountain. If the air is perfectly still, you hear a sharp, crisp beat. But if a thick fog rolls in, the sound becomes smeared and stretched. By measuring precisely how much that drumbeat has been smeared, you could calculate the total density of the fog along the entire path. A fast radio burst is our cosmic drumbeat, and the invisible intergalactic medium is the fog. By analyzing the exact dispersion of each burst, astronomers can perform a direct census. They can add up all the baryonic matter, all the protons and neutrons tied to those electrons, along a perfectly straight line that cuts across billions of light-years of space. This provides an independent, clean measurement of the universe's total baryon content, bypassing the need to look for faint glows or subtle shadows. The results from these cosmic yardsticks have been decisive. When scientists tally the matter revealed by the dispersion of many fast radio bursts, the numbers are starting to align almost perfectly with the predictions from the cosmic microwave background. The missing matter is not truly missing at all. It is simply hiding in plain sight, woven into the fabric of space itself, and we finally have a tool to prove it. Galaxies themselves are not the serene islands of stars they appear to be. They are dynamic, often violent, engines that actively participate in the cosmic cycle of matter. This leads us to a powerful clue in our search: the role of galactic winds and outflows. Deep within a galaxy, the life and death of stars creates tremendous forces. When massive stars explode as supernova, they do not fade away quietly. These titanic detonations blast shockwaves through their surroundings, heating surrounding gas to immense temperatures and driving it outward at speeds of millions of miles per hour. On an even grander scale, the supermassive black holes at the centers of many galaxies can become active, consuming matter and unleashing unimaginable amounts of energy as quasars or active galactic nuclei. These cosmic powerhouses can generate winds so ferocious they can blow an entire galaxy's reservoir of gas clean out into the vast emptiness beyond. Picture a forest fire on a planetary scale, where the explosive force of countless supernovae and the focused fury of a central black hole combine to create a hurricane of superheated gas. This is not a gentle breeze, it is a galactic-scale fountain, ejecting atoms that took billions of years to form into stars and planets, hurling them back into the void. Where does all this ejected material go? It does not simply vanish. These powerful outflows inject a colossal amount of normal matter, rich with heavier elements like oxygen and carbon, directly into the spaces between galaxies. This gas, now scattered and heated to millions of degrees by its violent expulsion, becomes a primary source for the very warm-hot intergalactic medium we have been searching for. The connection is profound. The small-scale processes within a single galaxy, the death of stars and the fury of black holes, are directly responsible for seeding the largest structures in the universe. They are the factories that manufacture and distribute the raw material of the cosmic web. This transforms our understanding of the missing Baryon problem. The atoms are not just passively drifting in the voids, they are actively being pumped there, driven by the relentless cycle of stellar birth and death. So the answer to where the missing matter went may not be a single location, but a continuous process, a great cosmic migration orchestrated by the galaxies themselves. The very gravity that binds galaxies together also provides the perfect hiding place for their missing atoms. Every galaxy, including our own Milky Way, is cocooned within an immense, invisible sphere of dark matter. This ghostly halo exerts a powerful gravitational pull, a force so strong it dictates the rotation of stars and acts as a cosmic trap for normal matter. As ordinary gas falls into this gravitational well, it does not simply drift in peacefully. It plummets at tremendous speed, crashing into other infalling gas and converting its immense kinetic energy into searing heat. This process, known as gravitational heating, can raise the temperature of the gas to millions of degrees, transforming it into a diffuse, hot atmosphere that envelops the entire galaxy. This is not the cold gas of star-forming nebulae. It is a giant, shimmering shroud of ionized plasma, so hot it glows only in high-energy X-rays and so thin it is virtually transparent. Our telescopes struggle to see it because it blends seamlessly with the background, a faint and elusive fog clinging to the edges of the visible universe. So the baryons are not lost in some distant, empty void. They are right here, hiding in the extended coronas of galaxies themselves, trapped by the dark matter we cannot see and heated to a state that makes them nearly invisible. This realization shifts the entire investigation. We are not searching for an empty locker. We are trying to see the very air inside a vault whose walls are made of shadow. The challenge becomes one of sensitivity. How do we weigh this hot galactic atmosphere, this ghostly corona, when its signal is a whisper against the roaring static of the cosmos? The answer may lie not in looking at individual galaxies, but in listening to the echoes between them. But the clues are not all found in the distant cosmos. Some of the most telling evidence arrives from within our own galactic neighborhood, carried by messengers of incredible energy. Cosmic rays are not rays of light at all. They are subatomic bullets, protons and atomic nuclei accelerated to nearly the speed of light by the shockwaves of supernova explosions. They race through the galaxy in a chaotic, tangled path, spiraling along the invisible lines of the Milky Way's magnetic fields. For our investigation, these particles are more than just high-energy radiation. They are intrepid scouts, and their journey holds vital information. As a cosmic ray proton travels for millions of years through the vast spaces between the stars, it occasionally collides with the nuclei of a much slower-moving atom, a piece of the thin interstellar gas that permeates our galaxy. These collisions are violent and rare, but they leave a mark. They can shatter the cosmic ray particle itself, transforming it into lighter, secondary elements like lithium, boron, and beryllium. The key is that the amount of these secondary elements we detect in the cosmic ray flux is a direct result of how much material the original protons have slammed into during their long voyage. It is a measurement of the total thickness of the galactic gas they have traversed. Think of it as a cosmic game of pinball. By studying the scratches and dings on the ball when it finally arrives, you can estimate the total number of bumpers and obstacles it must have hit along the way. By meticulously analyzing the chemical composition of cosmic rays, scientists can perform this calculation on a galactic scale. They can estimate the average density of the diffuse, invisible baryonic matter that fills the seemingly empty space within our own Milky Way. This provides a crucial, local piece of the puzzle, confirming that a significant amount of normal matter exists not as stars or cold dust, but as a pervasive, ionized gas right here at home. It is another independent line of evidence, telling us that the hidden reservoirs of matter are not just a feature of the distant cosmic web, but a fundamental characteristic of all galaxies, including our own. The shadowy Lyman-Alpha Forest was only the beginning of the story. To truly understand the nature of the hidden gas, astronomers had to learn to read its chemistry. When they look deeper into the light from distant quasars, they find a richer, more complex story written not just in hydrogen, but in the faint fingerprints of heavier elements. These are the metals of the cosmos, atoms like carbon, oxygen, and silicon, forged in stellar furnaces and scattered across the universe by supernova explosions. Their presence in the seemingly pristine intergalactic voids is a crucial clue. It tells us this is not just primordial gas left over from the Big Bang. This gas has a history. It has been processed, enriched, and violently expelled from galaxies, exactly as the models of galactic outflows predicted. Each of these elements absorbs light at its own unique set of wavelengths, creating a whole new set of absorption lines in the quasar's spectrum. The beauty of these metallic lines is what they reveal about their environment. The specific pattern of lines from an atom like oxygen, for instance, acts as a cosmic thermometer and barometer. By seeing which lines are strong and which are weak, scientists can deduce the temperature and density of the gas cloud with remarkable precision. A cloud that is too cold will not produce the right lines. A cloud that is too hot will have its atoms stripped bare, leaving no lines at all. The sweet spot, the condition that perfectly matches the predictions for the warm-hot intergalactic medium, is a searing temperature of millions of degrees and an incredibly low density. Finding the absorption signatures of ionized oxygen and other metals in the quasar's light, exactly at the expected energies for such a hot, thin gas, is like finding a signed confession. It confirms the identity of the suspect. This is not just any hydrogen cloud. This is the WHIM itself, a vast repository of matter that has been heated and enriched by the very galaxies it now surrounds. Each metallic absorption line is a data point, a direct measurement that helps us weigh this elusive component of the cosmos, bringing us one step closer to balancing the universe's ultimate ledger. Mapping the universe on its grandest scale requires a survey of almost unimaginable ambition. This was the goal of the Baryon Oscillation Spectroscopic Survey, known as BOSS, a project that meticulously charted the three-dimensional positions of over 1 million galaxies. Its purpose was to trace the cosmic web in unprecedented detail, to see the great walls and vast voids not as a blur but as a sharp structural blueprint. The key to this map lies in a fossilized imprint from the universe's infancy, a standard ruler etched into the fabric of space itself. In the first 400,000 years after the Big Bang, the cosmos was a seething plasma of matter and radiation. Pressure waves like sound waves rippled through this hot soup, compressing matter into a regular pattern of peaks and troughs. When the universe cooled enough for atoms to form, this pattern froze in place, leaving a specific, predictable scale imprinted on how galaxies would later cluster together. This scale is the Baryon acoustic oscillation, and it acts as a cosmic tape measure. By finding this characteristic spacing in the distribution of the galaxies mapped by BOSS, scientists could determine their exact distances from us and from each other. The result is the most precise three-dimensional map of the universe ever created, a chart of the cosmic web that reveals where the great rivers of dark matter flow, and just as importantly, where the vast reservoirs of normal matter should be pulled along with them. This map does not directly see the warm-hot intergalactic medium, but it tells us exactly where to look. It reveals the cosmic addresses where gravity has funneled the missing baryons, the dense knots and long filaments where the WHIM should be at its most concentrated. The successor to BOSS, the extended BOSS or EBOSS project, went even further, using distant quasars to map the gas in the voids themselves. Together, these surveys provided the ultimate treasure map for the hunt, turning a blind search into a targeted excavation of the cosmos's hidden architecture. These digital universes are born not in telescopes but in the silent hum of supercomputers, They are numerical simulations, entire cosmos crafted from pure mathematics and the unyielding laws of physics. Scientists program in the initial conditions of the Big Bang, seeding a virtual universe with the precise amount of dark matter, dark energy, and baryonic matter revealed by the cosmic microwave background. Then they press play. The simulation unleashes the force of gravity across billions of virtual years, watching as dark matter clumps into a vast cosmic web of filaments and halos. Ordinary matter, the baryons, flows along these invisible gravitational rivers, collapsing into galaxies and stars, but the simulation does not stop there. It incorporates the violent astrophysics of real life. Supernova explode with programmed fury, blasting gas out of galaxies. Supermassive black holes at the centers of virtual galaxies switch on, their immense energy pushing and heating the surrounding material. This is the crucial ingredient known as feedback, the cosmic pushback against gravity's relentless pull. When these simulations run their course, reaching the present day, they all tell the same story. They consistently show that a vast fraction of the normal matter, between 40 and 50%, does not end up in stars or cold gas within galaxies. Instead, it is predictably driven into the spaces between the galactic filaments. There, it is heated to temperatures between 100,000 and 10 million degrees, forming a pervasive, seething web. The simulations do not just vaguely suggest the WHIM exists. They provide a detailed, theoretical prediction of its exact properties, its density, its temperature, and its distribution. It is like having a time-lapse video of the entire universe, showing us exactly where the missing materials should have ended up. This digital prophecy gave observers the confidence to keep looking, to point their most sensitive X-ray telescopes and their fast radio burst detectors at the seemingly empty voids, knowing with certainty that the blueprint for the answer was already written in the code. Even the richest neighborhoods in the cosmos hold onto their secrets. Galaxy clusters are the true metropolises of the universe, colossal gatherings of hundreds or even thousands of galaxies all bound together by gravity. These are not serene places, they are dynamic, chaotic environments, and they contain a staggering amount of normal matter in the form of a superheated plasma that glows brilliantly in X-rays. In fact, the mass of this hot gas far exceeds the mass of all the stars in all the galaxies within the cluster. For a long time, astronomers thought they had a good handle on the baryon budget within these clusters. By measuring the total gravitational pull of the cluster, which comes mostly from dark matter, they could predict how much normal matter should be trapped within that immense gravitational well. Yet, when they performed the meticulous accounting, adding up the hot gas seen by X-ray telescopes and the stars in the galaxies, a subtle but persistent discrepancy emerged. The numbers were slightly off. There was a small but significant deficit. This was not the 50% missing matter problem on a cosmic scale, but a smaller, more localized version of it. How could these gravitational traps, these cosmic roach motels where matter checks in but never leaves, be missing any of their baryons? The answer lies in the violent life of the cluster itself. Not all gas is permanently captured. During the chaotic mergers of smaller galaxy groups to form these colossal clusters, tremendous amounts of energy are released. This can heat and eject some of the gas, blowing it out into the even more diffuse regions surrounding the cluster, a halo of gas so thin and hot it becomes virtually invisible to our instruments. Furthermore, the intense activity from supermassive black holes in the cluster's central galaxies pumps energy into the surrounding plasma, preventing some of it from cooling and falling inward, effectively keeping it in a tenuous, hard-to-detect state. So this small-scale deficit is a vital clue. It demonstrates that the process of hiding baryons is not a single event from the distant past. It is an ongoing, dynamic struggle between gravity's pull and astrophysical feedback's push, a battle that continually leaks normal matter out of the densest regions and back into the shadowy reservoirs of the cosmic web. Our eyes are blind to an entire spectrum of cosmic light. Just beyond the violet edge of what we can see lies the ultraviolet, a domain where the secrets of the hottest, most energetic gas are written. To read this hidden script, we needed to rise above our atmosphere, which blocks these crucial wavelengths, and deploy our most sensitive eyes in the void. The Hubble Space Telescope, famous for its stunning visible light images, also possesses a powerful ability to see in the ultraviolet. It was joined by a dedicated hunter, the Far Ultraviolet Spectroscopic Explorer, or FUSE, a satellite designed with one primary goal: to dissect the faintest ultraviolet light with exquisite precision. These observatories became the master cryptographers for the Warm-Hot Intergalactic Medium. They did not look for a faint glow. Instead, they once again turned to the brilliant light of distant quasars, using them as cosmic flashlights. As that ultraviolet light traveled across billions of light-years, it passed through the invisible filaments of the WHIM. The gas there, heated to temperatures between 100,000 and 1 million degrees, contains atoms of oxygen that have been stripped of most of their electrons. This highly ionized oxygen has a very specific appetite. It hungrily absorbs light at very particular ultraviolet energies. When the light from the quasar finally reaches Hubble or FUSE, the telescope's spectrographs break it down into a detailed rainbow. Scattered across that rainbow are tiny, dark dips, absorption lines that act as a direct chemical fingerprint. Finding a dip at the exact wavelength corresponding to 5 times ionized oxygen is like finding a signed name tag floating in an empty room. It is definitive proof that a cloud of this searingly hot gas, a thread of the cosmic web, exists exactly along that line of sight. Each detection is a triumph of persistence, requiring long observations and painstaking analysis to pull a ghostly signal from the noise. But together, these ultraviolet fingerprints have provided some of the most direct and compelling evidence that the WHIM is not just a theoretical phantom. It is a real physical structure, and we are finally learning to read its composition. Our own motion through the cosmos has left a unique fingerprint on the ancient light. As our solar system journeys around the galactic center and the Milky Way itself speeds through the universe, we are not stationary observers of the cosmic microwave background. This movement creates a subtle but measurable effect known as the dipole anisotropy. In one direction of the sky, the CMB appears very slightly warmer, and in the exact opposite direction, it appears just a fraction cooler. This is the Doppler effect on a cosmic scale, the same principle that makes a siren's pitch change as it races past you. For decades, this dipole was simply explained by our local motion. But what if that motion itself holds a deeper clue? Some scientists have proposed a fascinating possibility. The immense gravitational pull of a vast, unseen concentration of matter could be tugging at our entire galactic neighborhood, adding to our velocity. This would not be dark matter, which dominates gravity on large scales, but a massive reservoir of the missing baryons themselves. A nearby supercluster of galaxies, mostly invisible to us because its matter is in the form of that diffuse, hot WHIM, could be the unseen hand guiding our path. Imagine you are floating in a calm pond and you feel a persistent, gentle current. You cannot see what is causing it, but you know something large must be pulling the water. Our measured motion, when compared to the expected motion from the expansion of the universe alone, could be that current. The discrepancy, that extra push, might be the gravitational signature of the hidden baryons we have been searching for. This turns the entire missing matter problem into a kind of cosmic triangulation. By precisely mapping our motion and subtracting all the known gravitational influences, we could be left pointing a finger at the location of the universe's biggest secret stash of normal matter. It suggests the answer might be closer than we ever imagined. It's ghostly gravity already recorded in the oldest light we can see. The universe's greatest light show began with the first stars igniting in the darkness. This was the epoch of reionization, a cosmic revolution that fundamentally reshaped the very medium that fills space. For hundreds of millions of years after the Big Bang, the universe was a silent, featureless fog of neutral hydrogen gas. Then, in the hearts of the first brilliant, massive stars, something unprecedented happened. Their intense ultraviolet radiation began to flood the cosmos, and this light did not simply travel. It transformed everything it touched. Each ultraviolet photon was a tiny bullet of energy, powerful enough to knock the electron off a neutral hydrogen atom, ripping it apart into a separate proton and electron. This process, ionization, began to carve vast, growing bubbles of transparent, ionized plasma within the opaque neutral fog. Where did all this energy go? It was absorbed by the gas itself, heating it to temperatures of tens of thousands of degrees. This was the moment the universe turned the lights on, and in doing so, it turned up the heat on a staggering scale. The distribution of matter we grapple with today, the hidden web of hot gas, was set in motion by this primordial event. The reionization process did not simply clear a fog. It preheated the entire intergalactic medium, creating the initial warm foundation upon which later cosmic structures would build. The shock waves from the first supernova and the fierce radiation from the first quasars further stirred and heated this gas, pushing it along the gravitational contours of the dark matter web. So when we search for the missing baryons in the modern warm-hot intergalactic medium, we are seeing the final state of a process that began with the very first dawn. The great migration of atoms from cold, dark reservoirs into a hot, diffuse web was initiated by those first brilliant stars. Their legacy is not just the light they cast, but the enduring heat they imparted to the cosmos, a thermal echo that still determines where the universe hides its atoms. The evidence is mounting, but our current tools are straining at their limits, catching only whispers and shadows of the hidden web. A new generation of observatory is on the horizon, one designed with the explicit purpose of seeing the invisible. The Athena X-ray Observatory, a mission being prepared by the European Space Agency for launch in the 2030s, represents a quantum leap in our cosmic vision. Its name, the Advanced Telescope for High-Energy Astrophysics, hints at its profound ambition. Athena will carry the most powerful X-ray mirror ever constructed, coupled with instruments of breathtaking sensitivity. Where current telescopes like Chandra and XMM Newton must stare for days to gather a handful of photons from a suspected filament, Athena will see the same structure in minutes with a clarity we can only dream of today. This is not merely an upgrade, it is a transformation in our ability to perceive the universe. Athena's primary goal is to take the first true portrait of the cosmic web. It will not infer the warm-hot intergalactic medium from subtle distortions or faint absorption lines. It will map its sinuous, filamentary structure directly, tracing the glowing rivers of million-degree gas as they flow between the great clusters of galaxies. It will weigh this hidden component with definitive precision, finally answering the question that has haunted cosmology for decades. Is this where all the missing baryons have been hiding? The observatory will act as a cosmic coronagraph, blocking out the brilliant X-ray light from distant quasars and galaxy clusters to reveal the faint, wispy structures in the foreground, much like blocking the sun's glare allows you to see the delicate structures of its corona. With Athena, the faint shimmer of the WHIM will shift from a statistical ghost to a visible, measurable architecture. We will no longer be detectives piecing together a crime scene from circumstantial evidence. We will have a high-definition video of the universe's hidden circulatory system. This mission promises to close the case on the missing baryon problem by the 2030s, turning one of astronomy's greatest mysteries into a chapter in our textbooks and opening a new window into the energetic universe. The hunt for the missing atoms brings us to the very doorstep of the galaxies themselves. Every galaxy is cloaked in a dynamic, swirling atmosphere known as the circumgalactic medium. This is not empty space. It is a vast three-dimensional halo of gas, dust, and superheated plasma that extends for hundreds of thousands of light years, far beyond the visible edge of the stars. Think of it as a galaxy's extended weather system, a turbulent realm of cosmic fronts and storms. This region is a critical battleground in the life cycle of matter. On one side, gravity is constantly pulling in fresh, cold gas from the cosmic web, a pristine fuel for future generations of stars. On the other side, the furious winds from supernova and black holes are blasting processed material outward, enriching this halo with heavy elements. The circumgalactic medium is where this epic inflow and outflow collide, a chaotic interface that regulates a galaxy's growth and ultimate fate. For our investigation, this halo is a prime suspect for hiding a colossal amount of normal matter. The sheer volume of this spherical shell is immense, and its contents, while diffuse, add up to a staggering total. Current observations suggest that the combined mass of the gas in the circumgalactic medium of all galaxies could account for a significant portion, perhaps even matching the mass of all the stars inside the galaxies themselves. So the baryons are not just lost in the deep voids. A vast reservoir of them is held in this galactic exosphere, too hot and thin to form stars, yet too close and structured to be considered part of the distant cosmic web. We have been searching the far reaches of the universe, only to find that a king's ransom of missing matter is held in the extended atmosphere of every galaxy, a ghostly corona that is the final frontier before intergalactic space. Gravity itself can act as a cosmic magnifying glass, revealing the invisible. When light from a distant galaxy travels toward us, its path is not always straight. If it passes near a massive foreground object like a galaxy cluster, the fabric of space-time warps around that immense concentration of mass, bending the light like a lens of curved glass. This is gravitational lensing. The effect can be spectacular, stretching the background galaxy into luminous arcs and multiple mirrored images. But for scientists, this cosmic mirage is more than a beautiful illusion. It is one of the most precise scales in the universe. The degree of distortion, the specific shape of those arcs, is a direct measure of the total mass of the foreground object causing the lens. This measurement captures everything: the stars, the hot gas, and crucially, the dominant but invisible dark matter halo. So gravitational lensing gives us the total weight. Astronomers then perform a meticulous subtraction. They independently calculate the mass of all the visible components, the stars, and the glowing gas they can directly observe. When they subtract this from the total mass revealed by the lens, they are left with the immense gravitational signature of dark matter. But sometimes there is another, smaller gap. The total baryonic mass they can see, the stars and the hot cluster gas, does not quite account for all the normal matter that the gravitational pull suggests should be present within that dark matter scaffold. This is not the dark matter gap, it is a subtler baryonic deficit. It points to an additional, hidden component of normal matter that gravity is holding onto, but our telescopes cannot directly see. This missing mass within the mass is the ghostly corona of hot gas, the circumgalactic medium, whose gravity contributes to the lensing effect but whose light is too faint to detect. Each observation of this kind is like weighing a closed treasure chest. You know the total weight, and you can account for the weight of the chest itself, and a few gold coins you can see through a crack. But the lingering extra heft tells you there must be more treasure inside, hidden from view, waiting for a more sensitive scale to reveal its true nature. Even the oldest light in the universe is not immune to the pull of cosmic structures. As the ancient photons of the cosmic microwave background continue their endless journey, they pass through the great walls and voids of the cosmic web. These are not static landscapes. Over billions of years, the gravitational potentials of these vast structures have been slowly evolving, weakening as the universe expands and dark energy begins to dominate. When a CMB photon falls into a deep gravitational well, like a cluster of galaxies, it gains a bit of energy, appearing slightly blue-shifted. But if that well has become shallower by the time the photon climbs back out, it loses a little less energy than it gained. The net result is a tiny one-time energy boost. Conversely, a photon passing through a void that has deepened over time experiences a net loss of energy. This minuscule imprint, a fluctuation of just a few millionths of a degree, is known as the integrated Sachs-Wolfe effect. It is an incredibly subtle whisper, but it carries profound information. By creating a map of the modern cosmic web from galaxy surveys and then carefully cross-referencing it with the temperature map of the CMB, scientists can search for these specific correlated hot and cold spots. Where they find a patch of the ancient sky that is slightly warmer, aligned with a vast supercluster, it is a sign that the CMB photons received a boost from the changing gravity of that structure. This tells us something crucial about what is inside those structures. The strength of this effect depends on the total density of all matter, including the dark matter scaffolding and, critically, the normal matter woven into it. The elusive filaments of the warm-hot intergalactic medium, while ghostly, contribute their own gravitational pull to these cosmic potentials. A detection of the integrated Sachs-Wolfe effect is therefore an indirect measurement of the total mass in these vast webs, and by untangling the components, it provides another independent line of evidence for the presence of the missing baryons. It is as if we are listening to the faint echo of the cosmic web's own growth, an echo recorded in the fading warmth of the first light. Magnetic fields weave an invisible web of their own throughout the cosmos. While we often picture the universe's structure as shaped by gravity alone, these pervasive fields exert a subtle but powerful force on the very gas we are trying to find. They are the universe's hidden architecture, influencing everything from the collapse of a gas cloud to the journey of a cosmic ray. Their presence complicates the simple picture of the warm-hot intergalactic medium, turning a placid sea of hot gas into a turbulent, structured plasma. Magnetic fields can prevent gas from collapsing too easily, providing a form of cosmic pressure that supports the wispy filaments against their own gravity. They also channel and confine the sea of hot electrons, governing how heat spreads through these vast volumes. A region that might otherwise cool and condense could be kept diffuse and hot by the intricate dance of magnetic force lines. This has a direct impact on our search. The way this million-degree gas glows in X-rays or absorbs ultraviolet light is not just a function of its temperature and density. It is also shaped by the strength and orientation of its magnetic field. If our models ignore this magnetic influence, our predictions for how bright a filament should be or how strong an absorption line should appear could be completely wrong. We might be looking right at a dense knot of the WHIM and not recognize it because its magnetic field is making it behave in an unexpected way. Furthermore, these fields are the invisible highways for cosmic rays. They steer those high-energy protons along twisted paths, which directly affects our measurements of the galactic baryon content from cosmic ray spallation. A stronger magnetic field means cosmic rays travel a more tangled route, slamming into more atoms over their journey and making the galaxy seem richer in gas than it actually is. Untangling this magnetic web is therefore essential. We need to understand not just where the gas is, but the invisible forces that are sculpting it, confining it, and ultimately helping to keep it hidden from our view. The smallest galaxies in the cosmos hold some of the biggest clues. Dwarf galaxies, these faint, scattered collections of stars, possess a surprisingly shallow gravitational grip. Their dark matter halos are far less massive than those of grand spirals like our Milky Way, creating a gravitational potential well that is more like a gentle pond than a deep ocean trench. This fundamental weakness makes them incredibly vulnerable. The supernova explosions that occur within them, while fewer in number, can have a catastrophic impact. A single stellar detonation can easily blow a significant portion of a dwarf galaxy's entire gas reserve clean out into intergalactic space. There is simply not enough gravity to hold onto it. Furthermore, as these small galaxies orbit around larger hosts, they can be stripped of their gas by a process known as ram pressure. They plunge through the hot, dense atmosphere of their giant neighbor, and the resulting friction is like a cosmic wind blowing dust from a table, scouring away their remaining baryonic fuel. By studying what is left in these dwarf galaxies, and more importantly, what is missing, we gain a pure, unadulterated view of the baryon redistribution process. They are simplified cosmic laboratories. In a large galaxy, the complex interplay of forces can obscure the underlying physics, but in a dwarf, the effect is stark and clear. The violent ejection of gas is written in their very emptiness. Many of these tiny galaxies are gas-poor, their star formation having long since sputtered out because the raw material was so easily lost. This tells us that the process of moving baryons from galaxies into the cosmic web is not a gentle trickle. It is a rampant, ongoing theft, and the smallest, weakest galaxies are the first to be robbed. Their missing gas did not vanish. It joined the great, hot reservoir of the WHIM, a direct contribution from the universe's most fragile structures to its largest. A cosmic paradox lies at the heart of the universe's grandest cities. For decades, astronomers were puzzled by what they called the cooling flow problem. The centers of massive galaxy clusters are filled with an incredibly dense, hot gas that glows brilliantly in X-rays. According to all the basic models, this core gas should be losing its tremendous heat, radiating it away into space. As it cooled, it was expected to condense and flow inward in a steady river toward the cluster's center, providing a vast reservoir of cold fuel to form trillions of new stars. But when observers looked, they found a startling contradiction. The predicted deluge of cold gas and furious star formation was nowhere to be seen. The gas in the cluster cores was still hot. It was as if a boiling pot of water was refusing to cool down, defying the fundamental law of thermodynamics. Something was reheating the gas, actively fighting against the relentless pull of cooling, and that something turned out to be the most powerful engine in the universe. The solution to the puzzle came from the supermassive black holes lurking in the central galaxies of these clusters. These black holes are not passive traps. They are dynamic, cyclical beasts. As some of the hot cluster gas does manage to cool and drift inward, it falls toward the black hole, feeding it like kindling thrown on a fire. But this feeding frenzy does not last. The black hole responds with a ferocious outburst of energy, firing jets of relativistic particles and unleashing powerful shockwaves that ripple through the surrounding plasma. This is a cosmic feedback loop of breathtaking precision. The black hole acts as a regulated thermostat. A little too much cooling and inflow triggers a violent outburst that heats the gas back up, shutting off its own fuel supply. This process prevents the gas from ever cooling enough to form the expected flood of new stars. So what does this have to do with our missing baryons? This feedback mechanism is a masterclass in cosmic redistribution. The energy from these black hole outbursts does not just reheat the gas locally. It pumps tremendous energy into the cluster's outskirts, helping to push and keep vast quantities of normal matter in a hot, diffuse state within the cluster's immense halo and even beyond. It is a primary reason why so much baryonic matter remains hidden in these extended coronas, too energized to collapse and become visible. The cooling flow problem reveals a universal truth. The hiding of baryons is not a passive state. It is an active, ongoing process, a great struggle between gravity's pull and the explosive feedback from black holes, a battle that continually cycles normal matter between visibility and obscurity. This final clue pulls all the others together into a single, unified strategy. The universe does not reveal its deepest secrets in just one language of light. To find every last atom, we must become fluent in every dialect the cosmos speaks. This is the power of multi-messenger astronomy, a holistic approach that combines every tool at our disposal. It means listening for the ripples in space-time from colliding black holes with gravitational wave detectors like LIGO and Virgo. It involves catching the ghostly neutrinos from stellar explosions with underground observatories like IceCube. And it requires collecting every kind of light, from the long, slow waves of radio to the searing, short bursts of gamma rays, using observatories on the ground and in space. Each messenger tells a different part of the story. A fast radio burst gives us a clean measure of total electrons along its path. An X-ray telescope traces the hot gas glowing faintly in a filament. A gravitational wave signal tells us about the total mass involved in a cataclysm, independent of light. When we combine these separate threads of evidence, they cross-check and reinforce each other, building a composite picture far more complete than any single observation could provide. Think of a team of detectives, each with a different specialty, working a complex case. One analyzes fingerprints, another decodes digital records, a third studies financial transactions. Alone, their clues are suggestive. Together, they can reconstruct the entire sequence of events and close the case for good. Multi-messenger astronomy is our ultimate cosmic detective team. It is our best and only bet for finally balancing the universe's ledger, for accounting for every single proton and neutron that was forged in the Big Bang. The mystery of the missing baryons is not a puzzle that will be solved by a single, brilliant flash of insight from one instrument. It will be solved by a chorus of voices, each whispering a different part of the answer, until together they form a shout we can no longer ignore. From the cosmic ledger's stubborn imbalance to the faint X-ray whispers of the WHIM, each clue has brought us closer to the answer. We have traced the shadows in the Lyman-Alpha Forest, felt the searing heat of the circumgalactic medium, and followed the smeared signals of fast radio bursts. We have watched supernova blast atoms into the void and seen black holes act as cosmic thermostats, all while supercomputer simulations laid out the grand blueprint. The evidence points overwhelmingly to a single, sprawling conclusion. The missing half of the universe's normal matter is not lost. It is woven into a million-degree tapestry, the Warm-Hot Intergalactic Medium, strung between the galaxies in filaments too faint for our eyes but undeniable to our instruments. The upcoming Athena mission promises to transform this ghostly suspect into a detailed map, finally weighing the cosmic web with the precision we need to close the case. This is the power of human curiosity, a relentless investigation that has turned a fundamental discrepancy into a triumphant discovery in the making. The universe has been hiding its atoms in the most obvious place of all, the vast, hot emptiness between the stars. The mystery is not yet fully solved, but the path forward is clear. Stay curious, follow the light into the darkness, and watch as this great cosmic detective story reaches its final, breathtaking chapter.